All right, yeah. Good morning, everybody. Welcome. Last day. It's gone quickly. Today we're going to just have a kind of like a breakout session to start off with, get you guys to think about what kind of experiments are actually going to be good for understanding kinetics processes. And then we're going to go into looking at how real fuels are modeled and what are some of the things, the latest advances we have in actually modeling of the combustion chemistry of real fuels like jet fuel, diesel fuel, gasoline, and so on. But to start, I want you guys to maybe hook up in like groups of 2 or 3, and I'm just going to. We talked in this yesterday's lecture about these different types of experiments. There are a few more like counterflow diffusion flames, which can be used to measure extinction, ignition, and species. You have the slides for those. I won't go into detail about that. But we talked about some of the issues in like stirred reactors, in flames where you sample gases, also in shock tubes and rapid compression machines. And the idea was to give you some understanding of, even if you're a modeler, what you should be looking out for when you're looking at experimental data for comparison against your modeling. And also, if you're an experimentalist, what kind of information modelers need to make sure that the data that's being used is actually in a kinetically controlled regime and the physics of it could be modeled accurately. So I'm just going to skip to the last slide. It's kind of a problem I want you guys to rank. So I want you to just talk, take about 10 to 15 minutes, and then I want you to actually maybe make some sketches of these different experiments and think about if you were to rank these 5 experiments in terms of how good they are for the validation of kinetic models, and then explain why you think that's the case. So the first one is the ignition of a pool of liquid and measuring the gas species above the surface. Second one is measuring species from a large industrial ethylene cracker at a fixed temperature and pressure. The third and fourth are relating to shock tubes. The third is about ignition delay time measurements at some range of temperatures and pressures. The fourth about measurements of species time histories in a shock tube at again, similar temperatures and pressures. And the last one is a measurement of species produced above the surface of a non-porous catalyst in a packed bed laminar reactor at a similar range in temperatures and pressures as in the shock tube. So take about 10, 15 minutes, talk with your colleagues, and I want you guys to come up with your ranking of 1 to 5, the best for validation and perhaps the worst for validation of kinetic models. And of course, an explanation of that. Yeah, let's see what you guys thought. So anybody want to start? Who wants to say what they thought is the best experiments, perhaps, for kinetic model validation? All right.
Number 3.
Okay, you say number 3, which is the ignition delay time measurement. Okay, why?
A standard.
Okay, so it says a pretty standard experiment, range of temperatures and pressures. Anybody else agreed? You agreed? You agreed? You disagreed? Agreed. Okay. Okay. So, I agree. I agree. The third one. Remember, what do we say about shock tubes? There are issues, right? And measuring the ignition delay time has issues when the ignition delay time becomes very long, and that happens at lower temperatures. But here we're looking at pretty high temperatures, above 1,000 Kelvin. So, most fuels will ignite within a few hundred microseconds. So this is the sweet spot, yeah, for a shock tube. Above 1,000 Kelvin, pretty much you can't really go wrong with the measurement. And yeah, the pressures are pretty reasonable, 2 to 10 atmospheres. It's not like a very high pressure, 100 atmospheres or 200 atmospheres where, the shock tube might have some issues in its operation. Okay, I agree it's a good experiment. Who disagreed that it's the best one? Okay, how about you in the back? Okay. Why? Why did you say number? You said number 4 is the best one. Okay. Yeah, Dennis? He said the species produced in the time history, yeah?
No, there is no this one.
Yeah.
What type?
Yeah, also, okay, Dennis asked the question, what type of chemistry you want to look at? Actually, none of these would be good for low temperature. Yeah. So again, if we're comparing the ones up there, I think I would say number 4 also. Only reason is why? Because you, as you said, you measure the species. And what benefit does that give? Right? So she says even though the mechanism is somewhat wrong, you might get the ignition delay time correct. I mean, let's just say the fuel was ethane, C2H6, yeah? What might happen, this thing might break down, might undergo abstraction to make C2H5 plus, and with some radical, yeah? And then this one will undergo some kind of a fission reaction to make acetylene plus H. And then this ethylene might form another radical. And then this might go to form acetylene. And you'll be creating H radicals throughout this process. Here's an H radical. This one might react further again, form another H radical. So slowly, slowly, the H radicals are building up. Eventually, ignition will happen. And ignition will happen when there's enough radicals to drive the system to a runaway condition. So, of course, the ignition is dependent on the kinetics, but it's not, it's dependent on a complex series of reactions, yeah? It's not only, one single reaction which is governing the kinetics. You might also have the CH3 plus CH3 initiation reaction. And this main pathway of hydrogen abstraction may be the one leading to more radicals. This initiation pathway leading to 2 methyl radicals doesn't make hydrogen radicals, so it might be less competitive. But to get ignition right in any type of system, it's a global parameter of many different reactions occurring at the same time. And what really matters is what we call the branching ratio to different pathways. Pathway A should be 5 times faster than pathway B, and pathway C should be 2 times faster than pathway D, and so on. So you really need to get the ratio of all these different pathways, the branching pathways, and essentially at the end it comes to the branching to the radicals versus the branching to the termination, which determine does ignition happen. And that you can get right, yeah, even if you don't have the exact kinetic parameters right for every equation. I mean, errors might cancel out, the ratios might then give you the right condition that you get ignition. So again, it's a good ignition delay time. Is not a bad way of validating a model, but again, it doesn't give you individual kinetic parameters for pathways. Whereas the fourth one, again, if you're measuring something like you have a laser to measure methyl radical and you have a laser to measure ethylene, yeah, that's pretty common. They have lasers to measure methyl by laser-induced fluorescence. And then ethylene can easily be measured with laser absorption spectroscopy. So then you can actually measure this pathway's branching ratio versus the other. So then you constrain more than just a global parameter like ignition delay time to some specific kinetic pathways in the mechanism. So it's a bit better, yeah. But that's provided sometimes the laser has to be accurate, has to be available. Sometimes in a case like ethane to ethylene, and methyl, yeah, you have lasers. But for many other processes, we don't have lasers to measure the intermediates, species that are formed. OK, so yeah, 3 and 4, let's put them at the top. Maybe 4 is the best, 3 is the second. Then what would you guys say next? It gets a bit harder now. OK, what do you think? Okay. Okay. Anybody else agree with that or disagree? Let's talk about number 5. Who thinks it's a good experiment? Yeah? You guys think so? Okay. Okay, so this is a we say it says it's a laminar reactor. That's good. At least it's not turbulent. Laminar, you know the flow field fairly well. Okay? It's a catalyst in a packed bed system. So typically these are tubes with catalyst particles. And then you'll get this throughout the bed. Yeah, you might have a bed. Typically this bed in these types of reactors might be 10 millimeters. Yeah? Small bed of particles inside of a reactor. You bring in your gas, your reactants. And you measure out here with some GC or something, products. And it could be the same thing. You could have the same thing, ethane, C2H6, and you're using a catalyst, catalytic dehydration reaction. Catalytic dehydrogenation reaction. Yeah, this is called a catalytic dehydrogenation. You're removing hydrogen with a catalyst. And you can do it at much lower temperatures than if you did it thermally, if you had a catalyst. Okay, you measure the species coming out, and you try to determine the kinetics based on those measurements. Well, what challenges do you think might be faced in this kind of experiment? Yeah, so actually, at a macroscopic perspective, it looks like a nice experiment. But actually, at a microscopic perspective, what happens in actual kinetics on a catalyst? So around each particle, the reaction happens on the surface of the catalyst. Yeah? This might be a noble metal. Typically, though, we're using nickel, non-noble metals. Yeah? But it's some type of particle. And we say it's non-porous. That actually helps. Because if it's a porous particle, it looks something like this. It has all these channels, typical of zeolites and stuff. And then the reactions happen inside these pores. So what has to happen in either of these systems? For molecule to come and react at the surface, let's say the molecule is ethane. First, it has to come near the surface of the catalyst. Okay, that's a boundary layer phenomena. Around this catalyst is a boundary layer, so the molecule has to come near the surface of the catalyst, then it has to diffuse to the surface of the catalyst. So first process is what we call boundary layer diffusion. Then the second process might be adsorption or sticking of the molecule to the surface. Yeah, adsorption on the surface. Then as it absorbs onto the surface, you have then your reaction. Then you have desorption and leaving the boundary layer. Yeah? So around every particle is a rather complicated thermokinetic transport process. And then this happens around all these different particles. Yeah? So actually, catalyst kinetics are very hard to validate because we don't really know the physics so well. The boundary layer phenomena, you cannot get the transport, right? So we don't know the boundary conditions so well. We might know the boundary condition coming into the reactor, and leaving the reactor, we might know the overall flow is good, but again, where the kinetics are happening, the transport processes there are actually very complicated, yeah? And if you have a packed bed of reactors, it'll depend on the size of the particles, the flow rate, and also even the nature of the structure of the catalyst, yeah? And it's still not a bad experiment. In catalysis, it's actually one of the best experiments we have, because in other types of experimental configurations like honeycomb monoliths, it's even harder to know what's happening. But in catalysis, this is what we have. It's pretty hard, like in a code like Chemkin or Cantera, to write the code to simulate all these things. There are some groups that do it, like at Oak Ridge, in KIT, Karlsruhe, and others, yeah? And again, they have to know a lot about the catalyst. You have to know exactly these processes, like the boundary layer phenomena, the adsorption. So the catalyst particle has to be very well characterized. Then they put it into the reactor, and they do the experiments. Yeah. So there's another way to resolve this. We at KAUST do these experiments. Because, again, flow reactor experiments are nice. when there's no particles inside the bed? Can we think of a different configuration? Huh? Okay, well, also, one of the problems with this reactor is you might form carbon, coke, right? So as you dehydrogenate ethylene ethane to make ethylene, you're also making, this can eventually also break down to form carbon. So you form carbon on the surface of the catalyst. So there's other issues. And then you might deactivate your catalyst because it's not always the same over time. So you have to be very careful with that. We do an experiment. We take a very common experiment in combustion, yeah, the counterflow configuration. Like, you know, with counterflow burners, you can take a counterflow, you can put your reactant in here. And in a normal counterflow, we have reactant and oxidizer. Now we shut off the oxidizer stream. Instead of having a port which has gases, we have a surface which is coated with a catalyst. There's a catalyst surface. And the catalysts are not particles now, they're just coated onto the surface, across the entire surface. And then you heat this surface, so you govern the temperature as well. You fix the temperature of this surface. And what happens, the gas enters here into the bottom, and it goes towards the stream, and it forms a stagnation plane. Just like in a counterflow, if you had two streams flowing together, you have a stagnation plane, or a stagnation regime of the gas as it comes to the surface. Why is that good? Because once you have a stagnation regime, then you know the boundary layer, right? And then you can know exactly, you can calculate exactly the diffusion of the species, the reactant, to the surface of the catalyst. So that boundary layer phenomenon, which is rather complicated in spherical particles in a packed bed, you can figure out exactly. You can calculate it. And then you then also can deal only with the kinetic processes like adsorption on the surface, reactions on the surface, and desorption. And again, here you can use a laser. You can measure species above the surface. Some species will be produced and consumed. You can measure those species above the surface of the catalyst. So we take a simple configuration that we have in combustion, and we've taken this to the catalyst community, and it helps them a lot build models. Now, I said why. I told you yesterday I was against doing experiments only to validate models. Well, sometimes you got to do it, right? Some communities, they have no idea what the kinetics are at a global level, so they need these types of new experiments. And I think combustion people, we have a good capability. We have good diagnostic techniques, like lasers, temperature measurements. We have good experimental configurations which we can model exactly, and we can help other communities develop models for their fields as well. So the fifth one I think is a good one. I would maybe say you can do better, yeah, in catalysis and packed bed. But that is exactly, that experiment is what the catalyst community uses today largely, yeah, because they don't know really well. They're more into develop the materials and the material science and the catalyst, and they're less about developing, kinetic models which are used in industrial systems for validation. And that's where, you got to bring communities together to make real advances. What about the second one? Who thought about that one, Dennis? Okay, that's pyrolysis. Okay, so actually it's a bit simplified in that sense. There's no oxidation, right? So he says it's pyrolysis. It's a bit simpler. Anybody else thought about that one? Yes? Okay, good point. She says you might only get equilibrium composition, yeah? Yeah, what did you say?
Yeah. You only get
Okay, so number two, he says you don't have a catalyst, so that's a bit advantageous. Things will be closer to equilibrium, though, so it's not really a kinetically controlled phenomena. Yes?
It's a single temperature and pressure.
Okay, yeah. So it is single temperature, single pressure. Anybody know what an ethane, we say it's an ethylene cracker, but it's actually cracking ethane to make ethylene. So it's the same reaction that I've shown there. These are industrial reactors. They exist in many parts of the world. Probably a lot here in Texas and Louisiana, where the oil and gas industries are, the refineries. But anybody have an idea what this looks like? These kinds of reactors? Yeah? Okay. Yeah, it's a very big heat exchanger, actually. It's a shell and tube heat exchanger. Yeah, if you guys know what that, I mean, you just have, I'm very bad in drawing, sorry. Let's just say it looks like this. So this is a tube. You pass your gas, ethane, here. It enters this tube. It goes through these different pathways, and then it comes out. And it comes out as ethylene plus hydrogen, and then some minor products as well. And then outside of this is a shell. So this shell is where this is the shell, this is the tube, okay? And in the shell, you pass a very hot inert gas. Actually, they basically heat this thing with burners, yeah? They have natural gas that they're burning. And they're burning and they're heating up. They're making the CO2, water from the combustion, and that's going through the shell, and that's heating up the gas inside of the tubes. And this thing is huge. I mean, each shell and tube heat exchanger is about 60 meters tall and maybe 10 meters in diameter. So these are just massive heat exchanger reactors. And they might have 5 of these, and then they process millions of tons of ethylene a day, yeah, in these huge plants. So first of all, it says it happens at 1,000 Kelvin and 2 atmospheres. But many times what happens is there's always a gradient in temperature, yeah, because the burner's on one side, the hot gases are going up, the thing is 50 meters tall, so it's never a homogeneous isothermal reactor. They try to make it homogeneous isothermal, but it's not. So you don't really, and they might only measure temperature once every 5 meters, yeah, across the 50 meters of the height of this reactor. So that's a challenge, of course, with industrial systems, right? You don't really know what it is. And I agree, typically industry, they won't even care about the kinetics. They'll just say, we just assume equilibrium. We simulate this reactor as an equilibrium reactor, and we use that to design the system. But that's a problem because that works fine for like 1 month, 2 months, 6 months, but then every 8 months they got to shut down the reactor because there was carbon buildup inside, and they got to clean it out. And why is that happening? Because it's not equilibrium. There are kinetic processes happening inside, carbon formation in the hot spots of the reactor. So there's groups like in Milano, in Italy, in Ghent, in Belgium. There's a leading group on steam crackers. Actually, they actually mix ethane with water going in. It's usually, they crack together with water. Why would you have water? Well, one reason is because this is a pressure-dependent reaction, right? And water is a very good third-body collider. And yeah, this helps the reaction happen faster. The group at Ghent has pilot facilities, and yeah, they try to help industry understand better how to operate these types of systems. Yeah, I would say it's not the best for kinetic model validation, one, as you said, thermodynamics, but also the temperature is not very well known. There's many hot spots, and you don't have good measurements throughout the reactor. Ideally, what you would do is have gas probes at different points in the reactor system to measure species and temperature. And then you can say, okay, if you measured T and species here and here, and at different points, then you can start to build a model for this reactor. And what about the first one? Anybody have any thoughts about the first one? You said it was pretty bad. Okay, why? Okay. Yeah. But he says you're going to measure evaporation. He says you don't really know what's going on. You're just lighting a fire above a liquid. Okay.
Governed by physical effects and not kinetic effects.
You say it's governed by physical effects. Okay, not kinetics. Anybody doing something similar? You are?
Yep.
Okay, what are you doing?
Do Class B.
Okay, and you're using extinction pool fire. Where's that? Yeah, where are you doing that? Western Polytechnic. Okay, so how's the experiment again? Okay, oh, so you start, he says you start the fire, a pool fire,
Yep.
and then you extinguish it with nitrogen, and it's really as big as this? I said, okay, the fire is pretty big. So that's a very big fire and a very heterogeneous system, right? Many different, probably there's a lot of fluid mechanics effects. If the fire is so big, it's hard to get probes in there. So a pool of liquid, yes, the size of the pool will make a difference. You know, the experiment might even look as simple as this. You have a dish, and this is filled with liquid. And this could be something like a 20 millimeter diameter, so not a very big liquid, yeah. And then you can ignite, you know, some kind of a flame above the surface. The flame, okay. And the flame, if there's no oxidizer introduced directly to the stream, to the surface, it's going to be a pretty weird flame, right? Well, actually, the flame will look more like this, right? Probably something like that, a wrinkled flame, just collecting air from the outside, trying to entrain the flame, entrain the oxidizer to burn the liquid. It would be a pretty messy system, yeah? So, like, and that's how a typical pool fire might be. And then here it would be extremely difficult to if you measured species anyway at different points, it's going to be different here and here and here and here and the flame is moving all the time because the oxidizer stream around it is not, you know, carefully controlled. So it'll be a pretty messy experiment. But there's one group, okay, I mean, probably several groups that do this. They try to get the flame to be as well characterized above the surface, and how they do this is they impinge the oxidizer onto the surface, yeah? Again, in a counterflow configuration. So now the oxidizer is coming from a well-known direction. They know the flow rate of the oxidizer towards the surface of the liquid, and then they ignite the flame, okay? And you don't like it? Okay, oh, he says it's not a pool fire anymore. Yes, it's not a pool fire. So, yeah, again, it's not, I mean, none of the kinetic experiments we do are engines or gas turbines, but they try to represent some features of reality. Again, but the real guy who studies the pool fire says, that's not a pool fire, yeah? And I agree, it's not a pool fire anymore. But again, if you want to understand a bit more about some of the processes that are happening in a pool fire, this kind of experiment could be useful. The challenge still here, though, is even if you have oxidizer coming at a fixed condition and it's flowing towards the surface, you need to know the mass flow rate of the fuel, right? And that's pretty hard to figure out. But if you know the temperature of the surface, the temperature of the liquid, and delta H vaporization, yeah, then you can start to calculate. Then you know the heat of vaporization, you know the temperature. Then based on the amount of fuel is simply m dot delta H vape, yeah, and then you can figure out what m dot is if you know the temperature near the surface. And then you can start to say, okay, you know the amount of fuel here, you know the amount of oxidizer, and you can start to build a model for that. So a group at San Diego, Foreman Williams, you probably know the name, Sarathy, they do these kinds of experiments, counterflow, pool fire, or not pool fire, okay, counterflow liquid stabilized flame, yeah, to understand more about how liquids might burn. And of course, anytime you have a liquid burning, it's a combination of evaporation and then combustion. And so you need to decouple those processes or understand those processes as well as possible. Okay. So that's, I mean, that was good. You guys understand some of the major features that are required to get these experiments to be appropriate for kinetic model validation. Also, again, if you're designing experiments, new experiments, and we need new experiments, right? People are doing here plasma reactors. You know, plasma reactors, you got to operate them at a regime where you know very well the plasma's physics, so then you can understand the kinetics processes. People, I think some people here are doing solid combustion, like a wood fire, right? You're doing the, what was your experiment again? In Berkeley, sorry, I forget. Yeah, solid, it has a solid cylinder of wood, I guess, or plastics. Yeah, and then measuring the burning rate, which is very important, I guess, in many safety applications. Also to understand, groups in Berkeley trying to understand how wildfires spread. And again, a wildfire is a massive system. You can never really understand at a fundamental level looking at a big wildfire. So they take single pieces of wood, and they try to understand the burning rate characteristics, even the kinetics. But they have to very well control the process to make sure they can actually get interesting information out of it. Okay, so that's it for experiments. I'm going to start going into now the last lecture, which is about application of kinetics to understand real fuels. So all this time, we've been talking about the history of chemical kinetics, how people started developing the first kinetic models 100 years ago or so, then how we start developing models with the advent of computers for simple molecules like hydrocarbons and hydrogen and oxygen. And then we talked about things like heavy hydrocarbons that are found in real fuels. But all of this is still, you know, only in the last 20 years, we've started actually understanding how real fuels, like mixtures, every real fuel you have in a real engine is a mixture of many different species. And before 15, 20 years ago, we had very little understanding of how these mixtures behave. So this last lecture, I want to try to give you guys a flavor about how we can start to understand, you know, what's happening in mixtures and what are the approaches the community has and what are some of the recent advances the community has. So I think I'll skip the first few slides because we actually covered this in the first day. I highlighted how, you know, gasoline or diesel or jet fuel coming out of a refinery is a complex mixture. And as that fuel gets heavier, you know, you have different types of hydrocarbons present. And then also the kinetic models are, OK, I lost it here. And we tried to say how the models for light hydrocarbons like natural gas, the ones in natural gas are well established. But as we go to heavier mixtures like diesel and jet fuel and gasoline and even heavy fuel oil, the types of the models we have are very, I don't know what's going on. Let me just see why this is crashing. Maybe I'll close some other things. It keeps crashing on me. So we're going to try to skip that slide, okay? Maybe that's the problem. No. Okay, bear with me. We'll do it the easy way. I'm not going into slideshow mode, okay? Because that's causing it to crash. So we'll just do it like this for now. I'll try to fix it at the break. So those real fuels we said are complex mixtures. And again, here's looking at the types of hydrocarbons you might see in different types of fuels. So gasoline has C5 to C9. There's different types of linear alkanes and branched alkanes, kind of like the ones that we build the models for previously in this class. Isooctane, we have some cycloalkanes like cyclopentane, some double bonded species, alkenes, and aromatics. And if you go to jet fuel, the carbon number increases, C9 to C14. You see the linear alkanes become longer in length. The cycloalkanes start to have branches coming off the side, so like butyl cyclohexane. These are the same aromatics, monomethylated or dimethylated aromatic species, and even sometimes some fused rings. And then if you go to diesel fuel, well, diesel fuel, you have very little olefins, but you have very long chain alkanes, like up to C18, and anywhere from 12 to 20 carbon atoms. You have branched hydrocarbons of different isomers, and also more highly branched aromatics. So aromatics with multiple alkyl substitutions. And if you want to model these real fuels, what we essentially try to do is, in the real fuel mixture, we try to see what are the different types of hydrocarbons present, and then we build something called a surrogate, okay? Because the real fuel might have 200, 300, in the case of diesel fuel, 500 different species. So what we try to do is we try to build a surrogate, a representative mixture of the hydrocarbons that are there. And we typically follow what we call a class-based approach. So based on the different classes of hydrocarbons, the Peona distribution. So based on the alkanes or the paraffins, the isoparaffins or isoalkanes, the olefins or the alkenes, the cycloalkanes and the aromatics. You pick one or two molecules from each group, and then you build a model for those molecules. Okay, but this is challenging, right? One reason is, say I have a gasoline I got in Saudi Arabia. Another one has a gasoline that they got in Europe. Third person has a gasoline they got in California. 3 gasolines, they're all different, okay? Of course, they will never have the same composition. They will have a 200, 300 different species, and at different concentrations. Each gasoline will have different concentrations of those species. So then how do we build the model? Yeah? And nobody goes into the pump and measures the hydrocarbons in the gasoline exactly, yeah? So how, I mean, how does the industry then moderate and ensure that the engine has the gasoline that it requires? Anybody know? Yeah? Okay, so they use some standard measurements, RON and MON. Yeah, RON and MON is, here in US, RON and MON. In Europe, they don't even have the MON, right? I think they just have the RON. Only RON. Yeah, only RON. And so there's some different way even in which you specify the fuel. So RON and MON. What else? Yeah, so density, viscosity, vapor pressure, yes, depending on summer or winter gas in different parts of the world. So every fuel, we have something we call a certificate of analysis, which has a series of ASTM standard tests that have to be performed. That's required for jet fuel, that's required for diesel fuel, that's required for gasoline. Anything that goes to the pump has to undergo some certain test before it leaves the blending facility to be used for commercial applications. And that's all we have, right? We have in the ASTM standards for like gasoline, I think there's about 12 different tests you have to do. So the RON, the MON, the hydrogen to carbon ratio, some global measurements of Peona. So they don't have to measure every hydrocarbon, but they got to tell you how many aromatics are there, how much olefins, how much paraffins, naphthenes, and so on, because that determines some regulatory requirements around emissions. And other things are density, DCN, cetane number, derived cetane number is used in diesel fuels. You don't have RON and MON, you have cetane number, or derived cetane numbers. And another important one is the distillation curve. So the distillation curve the distillation curve tells you basically the mass fraction or molar mass concentration as a function of temperature. So you might start here and here around 30 degrees C and end around 200 degrees C. This is temperature, okay, in degrees Celsius. And what this curve tells you is it tells you, okay, you start heating up the mixture, you have some mass fraction of light hydrocarbons coming out. As you heat up more masses come out, and then at the end you might have a curve that looks like this. So this tells you, okay, at this amount, at 30 degrees C, so much of the fuel is evaporated. As you keep on increasing the temperature, more fuel evaporates. Eventually you reach something like 200 C, and maybe all of the fuel has evaporated. 100% of the fuel has evaporated from the mixture. And this curve will change depending on the nature of the hydrocarbons. The light hydrocarbons, like the C1, or sorry, the C3, the C5 will come out first, and then the heavy stuff like the C8 to C10 will come out at the end. So it's kind of like it's a distillation process. And again, they have to report this in the ASTM standard spec using a standard methodology because, again, for winter gasoline and summer gasoline, you need different volatility characteristics. So these are the things industry uses. So we know some information about the physical chemical properties of a fuel based on the ASTM standard methods. We can't go and measure, again, every gasoline, what's the composition. So that's one challenge. We have to rely on simple measurements, or relatively simple measurements, which are widely available for every fuel in the world, yeah? And that's for gasoline fuel, diesel fuel, jet fuel. Second thing is, you can never build a model for 200 components or 250 components. You need to, that'll take forever. One model, typically for one fuel component, might take 1.5, 2 years to build. The kinetic models, then to do all the experiments to validate that. So you need a palette. We call this a surrogate palette. So what the industry does, or what the modelers do, and then also working with companies like Shell and Exxon and Aramco that make the fuels, they build these kinds of palette of hydrocarbon species, okay? So you pick some representative alkanes in gasoline, butane and heptane. You pick some representative isoalkanes, isopentane, 2-methylhexane, isooctane. You pick some representative aromatics, cycloalkanes, and alkenes, and you build models for these. So groups like at Livermore, Galway, KAUST, Aachen, we build models for all these, say, representative compounds. We might have a surrogate. This surrogate is 3, 6, 10 species, okay? Probably you could have nowadays surrogates of about 15 to 20 species. And then you mix and match these components to reach a mixture that matches the representative target properties of your gasoline. So I can mix these components to match the HC ratio, the density, the octane number, the research octane number, the motor octane number, and to match a real gasoline. And then you can, say, start to simulate using this surrogate, which is representative of the real gasoline, the kinetics of it. And this is a code we developed about in 2015. It's just a simple optimization toolbox that you specify. If you have an ASTM standard specification for a gasoline, you put in those properties, and it will output a surrogate and a kinetic model. And then you can use that kinetic model in simulations of like gasoline combustion. And similar things have been made for jet fuel and diesel fuel. But it's, okay, it's a long process. It's hard. And then sometimes it's complicated because then you start adding ethanol into the gasoline, because in some states you have ethanol, and then some countries are now looking at methanol blended into gasoline, and then you got to increase the size of your pallet, and then you start talking about e-fuels that might have different compositions. So the process is possible. If you go to the literature, this is used. This is a process we used to design fuels for Formula One. Okay, Formula One is a bit easy because they don't tell you. I mean, the gasoline is not given by the formula. Okay, every team is allowed to make their own gasoline, but there's a formula that's required for the gasoline. There's a specification. It says that the gasoline has to have a maximum RON value of 98. A maximum MON, I think it depends on the year. They keep changing it, say 87. Okay, so they specify the maximum RON, maximum MON. So you know the upper limit of what you're allowed to achieve. Similarly, they tell you the HC ratio range, the heating value range. So they don't, it's no longer, your constraint is not a real fuel. It's a formula, maximum upper limits that are allowed. There's also a rule called the 540 rule. So that says 40% of the fuel has to be made up of components that are above 5%. Yeah? So that means you cannot have, you cannot just have hundreds of components. They said they want 40% of the fuel to be made up of components that are above 5%. So again, you put all this stuff, these constraints, in a simple code, and then you then go and build kinetic models for what you think are the best components to achieve these targets. And yeah, I mean, we identified mixture with cyclopentane, isooctane, another molecule that's shown here called tryptane, and then other things to meet the 540 rule to maximize, okay, the octane numbers, the heating value, which is very important, and so on. So you can use these things for fuel design. But for studying real fuels, again, that are widely used in the market, this approach has its limitations because, again, new components keep coming about, found in gasolines, additives like, again, ethanol, prenol, different types of alcohols, OMEs in diesel fuel, and that makes it more challenging. So in the last, say, 6 or 7 years, the community has started to try to find perhaps a more elegant way to understand real fuel combustion. Because there are limitations, even though the traditional process works, you can build kinetic models for pure components, you can mix them together, it's time consuming, it's computationally expensive, it leads to very big models, because each individual component might have several thousand species in its kinetics. You put them all together, now you have a huge model, which is very difficult to deal with in any practical combustion simulation, even for a CFD simulation. It's impossible to include the kinetics of all these things. So you do a lot of reduction, and in the end, you might defeat the purpose of what you tried to achieve in the first place. So in that sense, combustion communities start to think about how do we simplify this process. So this was a nice paper about 10 years ago from Stephen Dooley, who's now a professor in, I think, Trinity College of Dublin in Ireland. He was a postdoc here in Princeton, so Dooley and Dreyer, Fred Dreyer was a professor here at Princeton. They started to look at, again, understanding in real fuels what really matters in the combustion kinetics. So they were looking at jet fuel. And in jet fuel, there's 400, 300, 400 different components. What really matters if you want to predict things like the ignition delay time of a jet fuel, or the flame speed, or the ignition and the extinction, or the soot formation and the intermediate species. And they made a very nice pictorial representation of this. They looked at many different jet fuels. They built kinetic models for those jet fuels. And then they started to look at what are the similarities in the combustion characteristics for different types of jet fuel surrogates. And they said, if you have a complex mixture that has, alkylated aromatics, alkyl cycloalkanes, normal alkanes, branched alkanes, these are all mixed together in a soup. But what happens in a combustion process? These molecules are heated up relatively quickly to, say, 600, 700, 800 degrees Kelvin. They start reacting, and they break down to intermediate components. And these intermediate components are, of course, fragments of the parent fuel molecule. And eventually, these intermediate components break down to C4, C3, C2, C1, and then the small radical pool. And again, we always say the small radical pool, the rate of buildup of this pool, the concentrations of these species are what govern all combustion phenomena. The ignition times, the extinction, the flame speeds, the major species that are produced as well. And this, of course, can always be coupled with things like diffusion and mixing and turbulence. But from a kinetic perspective, they started this. The understanding came about already about 10 years ago that real fuels, sometimes you can simplify the understanding of their kinetics because the mixture, even though you have many different hydrocarbons, they quickly break down to a common set of intermediates, which are common in all fuels, right? And that explains also why a gasoline that has an octane number of 97 and a motor octane number of 87 in the US, which has a very different composition than a gasoline which has an octane number of 97 and a motor octane number of 87 in Europe, still behave the same in the engine, yeah? And that explains, even though kinetically the components might be very different, they have similar octane numbers, and that's all that matters. So somehow this measurement of octane number has been done at a condition which makes fuels behave the same way in the engine, even if they're different compositions. And again, from a kinetic perspective, we understand why that is. It's because the rate of decomposition of all these big intermediates to smaller intermediates is relatively fast. And then the rate limiting steps are here in the slow chemistry. So as long as you can get the branching ratios and the concentration of these intermediates correctly, you can start to predict very complex combustion phenomena for mixtures. And again, there's a lot of papers in this that came out in the last 10 years. If you're interested, in this subject, you can study it. Okay, so we'll take a break now. Maybe go have some coffee. And then we'll come back and talk more about this approach and again, further simplifications we can make.